Bismillah ar-Rahman ar-Rahim. Assalamu alaikum wa rahmatullah. Peace and blessings upon you all. Yes, students, last lecture we couldn't actually complete. That was about semaphores, okay? And actually, I didn't know where it was last time, but not a problem. We're gonna implement semaphores all the way here, where we read now the classical problems in concurrent programming, and there are three which we will talk about. One is the producer-consumer problem, one is the reader-writer problem, and one is the dining philosopher's problem. Okay, so we're going to take the producer-consumer problem, where we have a kind of buffer. Okay, and producer is producing something and dropping it into the buffer, and consumer takes it from the buffer. So how many things we need to take care of? Firstly, the mutex, right? Why? Because when producer is producing something and dropping into the buffer, at that moment consumer should refrain from accessing the buffer. So this buffer is kind of a critical section, and we should apply a mutex, a lock on it. So when producer produces something, it should lock it, and when it is done with that, only then consumer can consume it. Now that is the one thing. Second thing will be that producer should produce something. Okay, maybe this buffer is full, so there is no place to fill. So before filling, he should check whether the buffer is full or not, right? If buffer is full, then he can't fill it, then he may go to the sleep. And in consumer case, consumer should consume only when the producer has produced something. Otherwise it will be consuming something which is empty. So it should not for example, we have a cup, okay, and one person is dropping into it something and one person is consuming it. Okay, so when a person fills it, he should see the cup is already filled to the brim. If it is filled to the brim, it will spill. Okay, you should refrain from filling more. So from a producer point of view, you should see whether the cup is full or not, in this case the buffer. And in a consumer point of view, consumer should see that if cup is empty. If the cup is empty, what will he consume? He shouldn't be consuming an empty cup, so he should go to the sleep at that moment. So these are the three things which we need to take care of, and we can do all the three using the semaphores. Okay, but our buffer here, this can be either the unbounded buffer. Sometimes we have a large memory and we don't care about memory. The buffer is huge, or our input rate is not so high. So we say, to make our algorithm simpler, we have an unbounded buffer, but more realistically we have the bounded buffer. In unbounded buffer, we don't the producer side, we don't care that the buffer is full or not, because we know it's never going to be full. It's huge, and we're not producing that much, so it's not going to be full. So that problem we take off. Okay, so producer can produce at any moment he likes, but a consumer point of view, he has to check whether it is empty or not. If it is empty, he shouldn't be consuming an empty buffer, right? When producer produces something, okay, firstly you've got to have a mutex which will lock this buffer. When we produce something, only then a consumer can consume. Okay, so let's try see how we have a solution of unbounded buffer problem using semaphores. Okay, so in an unbounded buffer, we don't worry about the buffer. So for our, it's arbitrarily long, so nothing to worry about. We got two pointers, in and out. Out is wanting next item to be produced. Okay, if you see, these are the guys. Sorry, I'm talking about in is the next item to be produced, and out is something next item to be consumed. Say we have consumed this item, now this is to be consumed, so out will point to the B1. So these shaded guys are the slots which are produced by the producer. That's why in is being here. So initially in will be here initially, and out will be out of the buffer, right? So when you have produced something, so now you can put up into this slot and out will point to this now. Okay, initially out was pointing outside. Now you out is here, okay, which is being produced, okay, and later on you can produce more, and actually in will go here where you can put the next thing, okay. So when you have produced, you increment the out here because you have produced here something, and in was pointing to the first empty slot. Now it go to the next empty slot where you can fill up now, okay. When you have filled in here, in will go now to this, okay, which is empty. So in will point to something where you can put things in. Let me make it more clearer. Say for example we have an these guys, and initially outwards here, and in was pointing to the first empty slot. You put up the in a, for example, you produced a. Now in will point to the next empty slot. So in is where you can put in, which is empty, and out is going to be pointing something which you want to which you can read, produce, okay, actually consume, sorry, okay. Now in is pointing to the slot where the producer can produce something and drop into the buffer. Now you have produced something, you put the B, in will go here, okay, which is the empty slot. So in will also point to the next item to be produced, okay, and out is point to the next item to be consumed. So this is going to be consumed, not consumed yet, so it is stays. Say for example now consumer consumes A, so this is no more here. Now out will point to the B, and so on, okay. So in is here for the index 0 1 2, and out is at 1, okay. So how many elements we have? In minus out, 2 minus 1 is 1. So in minus out is the total number of elements to be consumed, or to be or which are in the buffer at any point, okay. Now we need here two things to be done. Producer is firstly producer can produce at any time. It is free to add because buffer is unbounded, so there is no limitation that like the cup will get filled or the buffer get filled. That's not a problem with the producer can come anytime and fill it, but the buffer can be accessed by the one process, either the producer or the consumer. So therefore we need a semaphore variable s as a mutex, okay, which will lock if producer has to produce something, it has to first see whether the semaphore is it has to lock it with the semaphore, okay. If it's already locked, it will refrain. Similarly consumer will come up, it will has to lock it with the semaphore if it is already locked, so it can't access the this buffer, right? And second thing is producer can produce anytime, but consumer has to see whether it is empty or not, okay. If it is empty, then it should not consume. So for that we need an n, okay. Semaphore n we talk need for signaling. I can say that if producer produce something, it will increment the n so that we see that hey, something is there, so we can consume, okay. So let's talk about that. Before that we just revise our wait and signal operations, right, which was in our semaphore. What is wait doing and what is signal doing? Let me tell you a very simplistic one that we say before doing a critical section we have to do the wait and signal, right? The wait is chucking the s value. If I can say until s is greater than 0, if s is greater than 0 or until it is greater than 0, then you're gonna do what? Then you do s is equal to s minus 1, okay, until it is greater than 0. You can go on and decrement it, right? If it's a binary semaphore, we have for example s equals to 1 initially. That means lock is free, you can access it, okay. If it is greater than 0, that means it's positive, you can decrement it, make it 0. S is equal to s minus 1, so s1 minus 1 is 0. So when the s is 0, that means you have locked it, okay. Otherwise you're gonna go for sleep, else you're gonna go for sleep, right? If it is not this thing, you can go for sleep. Or you can say here if s is greater than 0, then s is equal to s minus 1. else sleep. You can do it like that. Okay, and a signal, what you're gonna do is we're gonna wake up someone. Okay, if there is someone waking, someone waiting, if someone is waiting on a S, you can wake that up here, right? Or you simply do what? S is equal to S plus 1, increment the S. Okay, back to free, is it? So wait actually locks it, and signal actually increments. So wait decrements and signal increments. If we talk about this guy, when producer comes in, it should see firstly is the buffer but this is unbounded buffer, so we don't need to worry about is the buffer full or not, right? So we have to simply do what? When you come in, you have to wait on the S, is it? When the producer comes in, it will wait on S, so it will lock it. Okay, so it's going to lock the buffer. If consumer is consuming it, he must have locked it, then you are actually gonna go for sleep, right? Because only one process can access the buffer. Now if it is free, S is greater than 1, so when you do wait, let me write it wait properly, wait on S, so it will decrement it, S will become 0. Okay, and you can produce something, and then you can access the buffer and fill it. When you're filled in, you're gonna, for telling consumer that yeah it's filled, you're gonna do something with the N. So what are you gonna do with the N? You will actually signal N. Okay, you're gonna signal N. Okay, now N will be counting some for, because it can have the values the buffer we have. Okay, we produce something, we increment N. So what is signal doing? Signal is incrementing, right? So signal is incrementing, S is equal to S plus 1. Similarly here, N is equal to N plus 1, so N will become 1 in this case. So when the consumer comes in, if there was nothing, if N, initially N was 0, for example, so what will consumer do with the N? Okay, consumer will do wait on N, right? Because it will decrement if it is greater than 0. If it is greater than 0, initially it was not greater than 0, so it's gonna sleep. That means the buffer is empty. Okay, so initially, for example here, buffer is empty, so what will be in N? There will be 0. What will be in S? There will be 1. That is, lock is free. Say for example, before producer, consumer comes in, so what, before locking it, he will do wait on the S, so that it will decrement it, wait will decrement, and signal will increment, right? Remember? So now when consumer comes in, say for example consumer comes before the producer, so there's nothing to consume here, actually it's empty, so it has to first lock the buffer, so it will wait on S. Okay, that means it's being locked, so it will, what will wait do to the S? It will decrement it, so it will make it S 0, so S is now 0. So let me say this is S, so S is now 0. From 1 it has become 0, so it's locked. So even now if the producer comes in, it can't, it has to sleep. Now it has to do firstly, before accessing the buffer, it has now to do first signal on N. Should it do signal or wait on N? Just tell me. If signal increments N, so you can't do that as a consumer. You have to do what? You have to do wait on N. Now what will happen if N is 0? What will wait doing? If N this time, now in this case we're talking about S, it's any semaphore variable, now it's an N. If N is greater than 0, okay, then it is okay, then you can decrement it and go ahead. But it is not, in this case N is 0, so what will happen? The else block will come up, you gotta go for sleep, because there's nothing in the buffer. Okay, in other case, if producer comes first, it will lock it will lock it, it will do wait. Excuse me, something happened here. This guy, wait a second. Okay, when the producer comes in, it will do wait on S. Okay, semaphore, it will lock it. Okay, because S is 1 for initially, for example, and it will make it 0. It will make it 0, so it can access the buffer. Now it will do signal on, after producing something, it will signal on the N. Now N signal does what? So increments N becomes N plus 1. Okay, does it make sense? So let us see the complete algorithm, and then I will explain. So this is our algorithm. What we are doing here is, this is our buffer, for example. It is unbounded, so no need to bound it on this side. So what we are doing is in and out both are pointing to the 0. Okay, in is pointing to the 0, out is also pointing to the 0 location. So 0, 1, 2, 3, 4, and so on. Okay, now S is the semaphore used for the mutex. It is 1, that means free, and N is a counting semaphore which will be used for by the consumer and producer for signaling each other, and initially it is 0 because it is empty, buffer is empty. Okay, this tells us the buffer is empty, and this will tell us that lock is free. Okay, you can access the buffer, and in and out pointing both to the 0th location, right? We can put out outside also, okay, or in this case simple to make it simpler, we are putting in and out both to the 0. Not a problem. Now here we have a method called append and a method called the take. The producer will use this method to produce something, actually drop something into the buffer. Where will it drop? It will drop where the in is pointing. So this buffer is the B, the array name. This is the array buffer, okay, and its name is B, and B of n, you will drop something which you want to produce. The producer will produce V, that is to be dropped where in is pointing. You produce it, say for example A, we'll put A here, and you increment the in will point to this location, right? And so on. Similarly, we say take, when the consumer takes, and it first takes where the out is pointing, okay, and that b of out, and put that in the W, okay, and increment the out, okay, it will go out goes to the next slot, okay, now, and it will return the W that will be consumed by the consumer. So this is the producer process, the consumer process. So producer will have a repeat and forever. So while true do begin, what we did, this is the same as that, repeat forever. This is the loop, okay, and repeat forever. So producer will produce something firstly, okay. Now by producing, it doesn't mean it has the right to access the buffer. It has to first see whether the buffer is free or not. So it will wait on S. So say for example it came in the beginning and S was 1. Okay, in the beginning S was 1 here. As you can see, it was free. So wait will decrement it. If S is greater than 0, yeah, it is. It will decrement it. S will become, this is my S. S will become 0. So it's locked. Okay. If at that moment no consumer comes in, it will do the wait on S, and it is going to go for sleep because S is not greater than 0. Because wait says if S is greater than 0, then decrement it, else go to sleep. So if it is not in this case greater than 0, so if consumer comes in, it has to go at this moment here, it has to go to sleep. Okay, okay. Now we are doing wait on S, so we are successfully locked it. Say for example our producer process came in the beginning, so we have successfully locked it, and then we append that V. We put that V at the in where the in is pointing in the array, and put V there and in plus plus. Say for example I put up something here, some data, so I'm saying it D. I put the D here. So that's what the V was producing, the D. Okay, and now in will go plus, append will put D in the location B of n, that is here, and in plus plus, in is pointing to this now. Okay, now it has done that, it has produced something. Now it has to signal consumer that yeah, I have produced something, you can consume. So that's why we are doing, firstly we release the lock because we're not gonna lock it forever because we are done. So I will release the lock. How? I say signal S. That means I am saying in the signal I say S is equal to S plus 1, so S becomes now 1, so it is again free, right? Now consumer can come in and it can access it, and after that I will do signal N. What signal is doing is it increments the N. The N was 0 in the beginning, now N becomes 1. Okay, if N was 0 at that moment, this consumer comes in to do wait on N. So wait says if N is greater than 0, then decremented, else sleep, so it would have been sleeping. Now when it says signal N, okay, so it will actually here consumer will do first wait on N. That means it will see if the N is greater than 1 or not, because if N is greater than 1, that will tell us that in buffer there is something. If N is 0, that means buffer is empty, so we should sleep, we should not consume. Or if the consumer doesn't come, producer again comes, no problem, it comes, it will lock it here as variable, it will append the things to the buffer where the in is pointing. Say it has now put up f in here, and in plus plus in goes here, like here, okay, and then it will signal n again. Now n becomes n plus 1, that is 2, n becomes 2, okay. Now consumer can come twice, not a problem. If consumer comes once, it will decrement here wait on n, because it is greater than 1, yes it is, and then decrement it, n becomes 1. It will lock the buffer and then consume it, okay. After it release the lock here, it is releasing the lock here by signaling the s, and it consumes w, no problem. It can come again and does wait on n. Now n is 1, okay, and it can again lock the buffer by using the semaphore s, and it will consume that whatever it is by using the take method. While the out is pointing, it will take it and it will signal s, release the lock, and then consume that w. Now if it comes again, now n has hit the value 0 right here, because wait on n makes 1 now decremented to the 0. Now if consumer comes again, it will do wait on n. Now n is not greater than 1, so it's gonna sleep, so consumer will go in a sleep queue, okay. So consumer 1, say for example, is here sleeping. Now if producer comes in again, it will start producing. It will lock it first on a s, and it will append it. It will release the lock, and it will signal n by signaling n by n plus 1, okay. But before what it does, signaling does is, if somebody is sleeping, okay, you should wake it up, okay, otherwise it will do the n plus 1. But somebody is sleeping on that n, okay, so we have to wake him up. So we wake this up, guy, come on, you can wake up. So it comes out of this wait loop, and it will lock the buffer and take that value from the buffer which producer has produced, okay, and then it will release the lock, okay, and so on. Do you understand what I'm saying? Okay. Now here we got to take care of this wait of n and wait on s. If we do before wait on s and then we do wait on n, it can create a deadlock, okay. We'll talk deadlock in detail later on, but you can imagine here that if you do wait on s, okay, and then do wait on n, so what we are technically saying is like this. Say buffer was empty, okay, and n is 0. So if consumer does wait on n, wait on s first, so it locks the buffer, okay, so it makes from s1 to s0, so it locks the buffer, so consumer can't access it. And then if it does wait on n, n is actually 0, okay, so when it wait on n, it's gonna sleep because there is nothing in the buffer, okay, it's gonna sleep, so it will sleep here. So it will wait for somebody, for producer. The producer will come and actually do the signal on n, okay. But yeah, producer comes, but it does wait on s, but s is already locked by the consumer, so it is sleeping with the lock. That's the problem. Now because it's sleeping with the lock, okay, it's locked the buffer here, and after this n, it's waiting on the n, and it actually sleeps with the lock on s. Now producer thinks that consumer is there, I shouldn't be, because s is 0. So what's gonna wait on s do here for the producer? Producer when comes, it sees wait on s, that means s, if s is greater than 0, you can decrement it, but it's not, it's 0 this time, done by the consumer, so it's gonna sleep. So it will sleep and think that sometimes the consumer will come and wake him up, and producer will think, so the consumer will think that producer will produce something and wake me up, and both are sleeping, so they are in deadlock. Nobody will actually access. So we have to first do n. We have to see whether there is something in a buffer, and then and only then we can wait on s. So we can't interchange. That's the problem. Okay, and that's the problem. So we have to do first n, then s. Otherwise, it will be a deadlock. Now, if we say this is a bounded buffer, then producer also has to take care that the buffer is full or not. So now if the buffer is bounded, okay, so we got to have one more situation here, that this is the bounded buffer, that now we're removing the assumption that the producer can come anytime and produce. No, if the buffer is full, say for example buffer was 0, 1, 2, 3, so we have here say for example some k values, so let me call it the k values, okay. And if all the k values are filled, the producer can't produce it. So before producing, producer has to think about this: is the buffer full or not? So that is how we can say that is buffer full, that is k, or not. Okay, so what will producer have to do is we had firstly the S semaphore for mutex, that is by both producer and consumer to lock the buffer. And then we said we have the another buffer, another this semaphore. What was that? That was N, right? Wait a second. That was N, to see if something is there or not by the consumer. If producer produce something, it signals N or increments N, and consumer when consumers decrements N. And now we use another semaphore E, which will tell whether there is something in a buffer, whether buffer is full or not. So in the beginning, S will be 1, which tells us that lock is free, and in the beginning N is 0, which tells us in the beginning that buffer is empty. Okay, and in the beginning E will be equal to K, that means all the buffer is free. If it is equals to K, that means everything is free, all the K slots are empty in the buffer, right? So now producer will come up, he has to do something with the S. Okay, producer has what will producer do? Firstly, before locking it, it has to see whether this is empty or not, right? So he will definitely do wait on the E. If what is wait on E saying? Wait on E says if E is greater than 0, you can decrement it. Okay, now E was, say for example 3, you can say I will say like this: 1 2 3 4. Okay, say from 1 2 3 4. So E in the beginning was, that's K is 4. So initially E is equal to K equals to actually 4, right? So what will wait on E does? Wait on E means decrement the E. Okay, so make it now 3. So E will become 3. Okay, now this is again the counting semaphore, because it's having more than 1 values. So because binary semaphore will take either 0 or 1, and counting can take any many. So actually how many slots we have to take that much. Now E is equal to 3. Okay, after that, when it's done, you can lock now the you can lock the buffer by the S. Okay, when you're done, you will append something to the buffer. Okay, when you're done, then you can actually signal the S, release the lock, and then signal the N and tell consumer that I have put something. So that means you increment the S. So here you decrement the S from 1 to 0, so it becomes 0, and here you're releasing it, S becomes 1, and you're signaling N, that is N becomes 1. Okay, and E becomes here 3. Okay, now consumer, if consumer process comes in, or producer can produce again, not a problem. Okay, so it will do what? If producer comes again, we have talked other things, let us talk about this E now. If the producer comes again and again, when will producer stop? Actually, producer comes again, he will do wait on E, that means he will make it 2. Okay, now he can wait on S has become back to 1 here, so it will decrement it, make it 0, that means locked, append, release the lock, and signal N becomes 2. Okay, and if producer comes again, it will do wait on E, it becomes 1, lock the buffer, append something to the buffer, and release the lock here. Okay, and then signal again 3, because we got now 3 elements. Now it again wait on E because it's greater than 1, so we can do it. Now it is 0, and you can lock, append, release the lock, and signal. Now we got 4 elements in the buffer, say for example A B C D. Now the buffer is full. Okay, now because we see the E variable has become 0. Now if we do wait on E, now wait on E does what? It will it can't decrement it, because we say when it is positive then decrement. I'll sleep. Okay, this is what wait does. If you don't remember, I will go back to the wait operation. If S variable is a semaphore variable, now this time E is our variable. Now if E is greater than 0, then decrement it, else sleep. But it's not greater than 0 this time, it is 0. So what should we do? We're gonna go sleep. So that will do the signaling for us. That will say if Now here, because the buffer is full, we're gonna go to sleep. Okay, now consumer can come in only, and he can consume all the 4 elements, okay, until n hits 0. Does it make sense? So let's see the full algorithm. So only change we do is we have here the e, is it? This is e, another semaphore, counting semaphore, which is equal to k. K is actually the buffer we have, the size of the buffer we have. Okay, it's a full. K means the full buffer. Okay, initially we have all the slots empty, so that's why E is holding the K. The producer, before producing anything, before appending it, you can produce, no problem, but you can't append it, the buffer here. Before you do anything, you have to gonna wait. You're gonna do wait E, right? You're gonna do wait on E, that semaphore E. Okay, so that we can understand that whether there is empty slot or not. In the beginning there is a 4 empty slots, no problem, you can decrement it, and then wait and append and signal usually, and then signal for n plus 1, make it n plus 1, and so on. And consumer process remains same. It has to do wait on n to see whether there is something or not. If producer has produced something and will be having something more than 0, greater than 0 values. And here consumer actually will see firstly, is n greater than 0 or not. If it is not, it's gonna sleep. If it is greater than 0, that means something is there. I can access it, then lock the buffer, take it, and release the lock here again. Okay, this is actually lock it, and this is here release lock. Okay, and also you can do the signal E, that this is the added thing, because now you have consumed something. Say there was something 3 things A, B, C. Now say for example consumer has consumed this, so this is a free slot now. Okay, so if there was only 1 slot left, so E must be having value 1. Now E should have value 2, because we have 2 slots. That's why we are doing signaling E. That's E is equal to E plus 1. That is, it will increment the E to 2, because we have 2 slots now. Okay, so consumer consumes something and it increments E as well, so that it does the signal on E. Okay, then you can consume whatever there is in a W. Okay, here. So this is the same, rest is the same. Only thing is, for the bounded buffer we need to first have another. So we have 1, 2, and 3 semaphore variables. E will tell us whether the buffer is empty or not. N will tell us whether there is something in a buffer or not, and S is used for the mutex. Okay, now if you're not getting it, just go back, rewind the video, watch it a couple of times or more times, any many times you like, and hopefully you will get it. Okay, so this is the end of this segment, so I'm gonna say bye bye. Hopefully this benefits you. So until next time, ma salama.